Wait a couple minutes here. Let's see who else logs on. Well, just a little over a week, and this will be behind us. And we can look forward to next fall. I don't know what the summer school situation is yet. I guess they may possibly have some online classes. But probably will, I guess, but I would doubt very seriously there'll be face-to-face classes. Good morning, Alexis. Let's see, I'm going to make this screen bigger. Okay, and we can get this out of the way. Yeah, hopefully you can see that. All right. One more minute, and we'll just see if somebody else logs on. And when you guys need to go, because this may drag on longer than an hour, so please don't worry about just, when it's time for you to leave, if you need to leave, whether it's another class or whatever the reason, just log off. You don't have to tell me, and you don't have to worry about you're leaving the session. And I haven't been as good at posting all of this as I want to be. Not nearly as good as I've got some videos made that haven't been posted yet, but absolutely this one is going to get posted immediately today after I'm done. Again, it may be more than an hour, but this will be on Blackboard, and so if you do miss the last portion of it, you can go back and watch it. But so what I'm doing today, I'm just going to do the homework problems that I assigned on Friday. Let me say that I assigned those kind of hastily. They're good problems, but when I looked at them, I didn't realize the first four. I thought when I looked at them that we were just writing the properties down from the standard form of the equation. And then I got in and I saw where the problem wants you to graph it. So I misspoke on saying that would take you 15 or 20 minutes to do. It's obviously much longer than that. So that's my bad. I apologize for misleading your expectations on that. Having said that, it is an important topic, the standard form, and you get the most out of it when you see the graph and the equation together. Then those different coefficients and parameters make sense to you. And if you go through the labor of drawing the graph yourself, then it really drives the point home. You really see it, because you could flip that book open and look at 4 or 5 graphs and look at an equation and say, okay, I see that, I'm done. And probably you do understand it, but you will not retain it. When you look at that a year later, you're taking calculus and you've got to know what the period or the phase shift of a function is, you won't recall it. If you've drawn the graph a few times, that'll help cement that knowledge in your brain. So it's not a waste of time doing that, and we're not going to cover as much material as I had wanted to this semester. We're just about done. We are going to talk about inverse trig functions. So I'm going to put some more on here about those, because you have to be introduced to inverse trig functions. There won't be a lot of homework on those. It'll be pretty straightforward. I think you'll be pleased with the coverage of that topic, and then we're done. I see Tucker saying, what's the final situation looking like? I'm still mulling that over in my mind, Tucker. I tried to register Friday online so I could upload a final to this ProctorU, and there's a little delay. It's like I register and one of their reps has to contact me before I can do the next step on it, of posting the exam. And so I'm still waiting on their rep, but the final is going to be next week, beginning Monday or Tuesday. And I'm still considering whether you guys that have been logging on here and doing all this homework need to worry about the final or not. I'm still mulling that over. So I'll try to get back with you soon on that. Just telling people, well, you don't need to take the final is a little problematic for some other reasons, administrative reasons that. But I do understand some people are put more effort into it than others, and you guys are showing that you're motivated to do this. So I do appreciate that, and your grade will reflect that, in whatever the case. But just give me a little bit longer on the final, and we'll see. Try to tell you midweek if you need to take it or not. Tucker says, will I be penalized for my homework? I don't understand exactly.
What I mean is, on my homework,
Yeah.
where you said that you didn't realize that we had to graph the things, those few questions you assigned us.
Right.
Will I be penalized for not graphing those?
No, what I'll do is I'll extend the due date. Okay. And I would like you to graph them, but they don't have to be done by tomorrow night. But anyway, I've got all the solutions here, and I'm going to cover them in this video, so you can work through it. That'll save you some time, perhaps. Maybe you don't have to write every single step, but you can look at these solutions, go through the process on one of the problems, because I want people to know how to graph it so they could make a graph themselves. And so you can read through the solutions, and this video will explain the step by step, and just draw the graph if you would, and write the equation next to it. Okay, that would be good enough. Does that make sense?
Yeah.
Okay. All right, I'm going to go ahead and start here. I think we're not going to get any other people logging on. So Friday, I gave Friday morning, I gave some problems to write down their characteristics from the form of the equation, to write down omega, which is angular frequency, the phi, and then the phase shift, and the amplitude, and also the vertical shift coefficient. So I'm going to go over all these now in these graphs, and we can kind of get an idea where this standard form helps us to think about these functions and view them. Okay, so the first problem, it was just y equals 3 times sine of x. Okay, now sine of x, hopefully everybody knows now, is just a basic function, and let me draw it out here. We should have a good idea in our head what one cycle of sine of x looks like. The two most important trig functions, by the way, are sine and cosine. So if you know those really well, you can develop all the information about all the other trig functions, okay? So the sine function is basically this. So I'm going to say f of x equals y equals sine, and I'm going to say x here, okay? So this zero crossover point always happens at pi, so this is 2 pi. And then it is a linear thing, so if you split this in half, half this distance is half of pi, so this peak occurs at pi over 2.
I would like to interrupt you here real quick.
Yes.
Alexis, if I pronounced that right, said, could you use this homework set we are doing as the final? As a question.
Yeah.
Not as a statement.
Yeah. Well, no, because I have to have some idea, your recollection of other topics in trig besides this, but don't worry about the final, okay? I'll make some kind of special arrangement with you two because you've been able to log in here consistently and stay with this stuff. So your final will be relaxed. Maybe I'll have you write a short paper on some other topics for review, something like that. So don't worry about the final. But I can't just say this homework set is the final. So getting back to the function here, you want to know these two basic functions. You want to know sine of x and cosine of x. And cosine looks just like sine, except there's a horizontal shift. If you move this function over to the left by pi over 2 radians, so just imagine now the starting point. Imagine this starting point is 0 instead of pi over 2, then the cosine function would have this form, and it would come on up here, dot, 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 and stop up here. And this out here would be 2 pi instead of this point. So the cosine function looks just like the sine function. There's just a phase shift involved, okay? And that's why both of those functions are called sinusoids. And there's a very interesting property of sinusoids that you can add any two sinusoids together, okay, as long as their frequency is the same. And frequency we can think of as omega, right? The angular frequency. So you can add any two sinusoids together as long as they have the same omega, and the result is another sinusoid. And that's a very, very interesting property because there's no other waves that you add together and you always get the same shape as the original shape when you add them together. And what's really interesting to think about there is that the two different sinusoids can have completely different amplitudes. They can have different phases. There can be a phase shift between the two. So you could add a sine function with any amplitude you want to a cosine function that has any amplitude you want. And then you can even throw a phase shift on either one of those. And when you get the resultant function from that, it is a sinusoid and it has the same frequency as those original ones. So its shape is identical to the shape of either one of those. Now that's a fascinating property that's used extensively in physics. There's a thing called Fourier Analysis, and you can basically model um, uh, any periodic function can be written as some sum of sinusoids. So that's another property, but a very general, powerful property. So any kind of periodic phenomenon you're tracking in nature, you can write it no matter what the shape of it. If it's periodic, if it repeats, it can be written as a sum of sinusoids. So anyway, that's just a very small, I wish we had more time. What I worked in for 30 years was chemical laboratories and steel mills. And we did lots of chemical analysis and used a lot of different kinds of lab instruments, different kinds of spectrometers. And the chemical analysis ends up being based on, in a lot of cases, is properties of sinusoids, believe it or not. So what happens in a spectrometer, just to give you, I know this is not working these problems, but I just want to show you where trig comes into play in many things that you wouldn't ordinarily think about. But when you look at electromagnetic radiation, okay, oftentimes that's modeled as sinusoids or a sum of sinusoids. So it turns out that when you excite an element, say take any element from the periodic table, carbon, but any element, when you excite that element, you add energy to it in some way, then it will give off energy. So when it goes into a relaxation state. So what you're doing is you're elevating electrons to a higher energy level when you add energy to an element. And as those electrons go back to their ground state, as they drop back into their relaxed configuration for that element, they emit radiation. That radiation is sinusoidal. It has a frequency, it has an omega, and depending on that omega, that causes it to reflect off of crystals at different angles depending on what its frequency is. And so we exploit that in chemical analysis with spectrometers, and you can excite a substance with radiation, and you can do that in many different ways. I could talk a long time about that, but when that radiation gets emitted from this material you're looking at, it's got a range of frequencies, and you can spread those out. Think of a prism in the same way that a prism does, except you use a thing called a diffraction grating. But you basically spread out the radiation from that material into a lot of different angles, and that's what trigonometry is all about, is angular information. And so based on the angle that that radiation leaves that material at, you can determine its structure, its molecular structure, because you now I'm getting way off the problem subject here, but basically there's two different phenomena. There's diffraction which has to do with how tightly the atoms are packed together in a material. And so you have you can think of it as a lattice structure, whether you have a certain spacing between molecules or between atoms. And because of that spacing, radiation will reflect off of that at different angles. And you can measure those angles and measure that radiation and determine what elements are present in a material and also their quantity. So that's called diffraction analysis. But then there's emission phenomenon, where the atom itself, again, when an electron drops from an excited state to a rest state, it emits a photon, and that photon has a certain frequency, a certain omega associated with it. And that omega will come off, depending on what omega is, it causes that to reflect off a crystal at different angles. And so you measure where those reflections occur at, and you get a list of elements that are present in this material, and then you measure the intensity, which would be amplitude of the radiation, and you have a math model that converts that into a percent concentration. So anyway, so trigonometry comes up in all kinds of modern day chemical analysis. And then, of course, with computers now, that can all be done very, very fast. And so you can take this, somebody brings in a rock and you hit it with an X-ray, and you're not using the X-rays to show you the physical structure of the rock. You're using the X-rays to give you a chemical analysis based on radiation that's re-emitted from the material and at what wavelengths it's re-emitted at. Okay, I know that's off topic, but I just wanted you to see some of the scope of trigonometry, how it comes into play in a lot of things. Okay, so the sine function is a function that you want to be very aware of. And the cosine function, because if you know these two simple functions here, you can, I'll draw it out here, that's sine. You can get a lot of the properties of the other trig functions, right? So the cosine is like a sine function that's just phase shifted. So it's like you just have a difference. Like if you start here on the sine function and then continue this until you get one complete cycle, until you get to this same value again, continue, that would end up here, then you have a cosine function. So you can see that the sine function and cosine function are really the same thing. There's just a phase shift involved with those two functions. Okay. All right, so back to the actual homework we're doing here. A simple sine function. The only difference in this equation is we're multiplying times a factor of 3. And from our standard form equation, a would be this factor of 3. This a coefficient would simply be 3. Our phi in this equation is 0. We could rewrite sine of x as sine of 1 times x plus 0, because 1 times x plus 0 is still just x, right? So this has the same value as this does, but now it's written in a form that we can recognize, and we can read off parameters we're interested in very easily. So here we see the omega for this would be 1 from this form, and phi, which is this angle that's added to omega x, is actually 0 here. Okay, so it's not that we don't have a phi, it's just that it's 0. We have one, but it's 0. And we do have an omega. You don't see it there, but that's because 1 times something is equal to something. It doesn't change its value. So if you only have a variable by itself, you have a coefficient of 1 in front of it. So that's pretty much that problem. Then you graph that. Again, it's just a simple sine function. The only difference being instead of an amplitude of 1, the amplitude is 3. So the peak height is 3 and minus 3 here. Okay. And there's no phase shift, so it starts at 0 where a regular sine function starts and ends at 2 pi. It's just the only difference between it and a very simple sine function, if you can there, is just that it has a 3 times. Okay. The next problem is a little more involved. Okay. Y equals minus sine times x plus pi over 3. Going back, I want to show you here. So let's graph y equals minus the sine of x. What does that look like? And it's just a mirror image, right, of the sine function. Okay, so this negative sign just flips this pattern across the x-axis. This is x. This is always x and y, okay, for what we're doing. We're always looking at the xy coordinate system. So a negative sign on a function reflects that function about the x-axis. So if you, like a mirror image, look at it, this is what the negative sign does to that function. Okay, and also notice here, think about our standard form, this would be equal to a sine x, right? So here a, which is the amplitude, is equal to negative, well, a is not the amplitude. A is this coefficient is negative 1. Amplitude is the absolute value of A. So the absolute value of negative 1 is 1. That tells you the peak height. And it's in both directions, right? So this is still 1 and 1. Okay, so that's what the negative sign is. It just reflects it over the axis. All right, so then we've got to deal with, we now have x inside. And remember, we call this thing the argument inside the parentheses of a trig function. This is called the argument of the function. And the meaning of argument is, an argument is something that gives you information about something else. That's what argument means. So this quantity here, which is this whole thing, x plus pi 3, gives you information about the value of this whole function. So this tells you the sign of what? The sign of this particular thing. So that's some of the reason behind that language. And it's written, sometimes you just see ARG and in a bracket. So that means this is kind of, the argument's kind of a function itself on this function, but it's very simple when it just means the value that's inside the parentheses. So the argument of sine of theta is just theta, okay? And again, sometimes it's just written ARG. The other thing I want you to notice here in a trig function, which you probably already know this, sorry, I keep thinking you can see this whole paper and you can't. But anytime you have a trig function, when you have, and when I say trig function, I'm talking about the circular function. So there's 6 of them, right? Sine, cosine, tangent, cotangent, secant, cosecant. For all 6 of those functions, you'll have that function in a parentheses. So the argument is always an angle, all right? And that's what trigonometry means, all right? The trig, the TRI, is 3. So you're talking about triangles with trigonometry, right? And then there's a word, it's called Goniometer, is a German word that means angle. Okay, so TRI, 3, and goniometer, and goniometer actually means measure of an angle. That's what it means. So it's the measure of 3 angles. So trigonometry is the study of triangles, okay, and a lot of different properties that triangles have. And these functions, sine, cosine, arise because of that right triangle that's formed when you travel around the unit circle. So that's where that word trigonometry comes from. And in spectroscopy and chemistry, a thing that measures the angle in these spectrometers, which uses some very sophisticated technology, is called a goniometer. And it can measure an angle, or it can dial in, it can set things, it can put a detector at a specific angle. So it's maybe a very highly controlled motor mechanism that turns a pivot that calibrates to some very precise angle. So that's goniometer. Anyway, the thing inside the parentheses is always an angle, okay? And so to graph this now, minus sine of the quantity x, minus sine times quantity x plus pi over 3. We look at our standard form, which is a sine omega x plus phi plus b. We see that a is -1, right? Because this is the same thing as -1 times sine. So we know our a coefficient's -1, which tells us our amplitude's absolute value, -1, is going to be 1. So the peak height on our function is going to be 1. Okay, we're in standard form here because this is omega x plus phi. Notice here we only have an x, so it's understood that this is 1 times x, so we still have omega. It's just its value is 1. And remember, the units on omega are radians per unit time. Okay, and then we've added another angle to this x here, and this angle that gets added in standard form, since it's an addition, is called phi. It's spelled phi. So this is not theta, right? Theta's got a horizontal line. It's phi, the Greek character phi. And so we write that down. Phi would be pi over 3. And then the phase shift is negative phi divided by omega. So our phase shift is negative pi over 3 divided by 1, which is just negative pi over 3. Okay. And then from our standard form, this b coefficient here, we don't have anything outside of this sine function, but that's the same thing as plus 0. We are adding something, but the something we're adding is 0, right? So b is 0. So, and that tells us we do not have any vertical shift in the function. So here the function's plotted. And so notice the amplitude is 1, which we got from our -1. I have to go back. We got our -1 is a, right? Here's a sine theta, -1. So our amplitude's 1. Our phase shift was negative pi over 3. Well, if you look at this graph, what did that do? Now remember, when we had negative sine function reflected what the regular sine function looks like across the x-axis. So that makes it look like an upside down sine function, the fact that we had that negative sign. Okay, where a was -1, that reflects it across this horizontal axis. The phase shift moved this function. Instead of starting at 0, where negative sign would start, it moved it exactly by the amount of the phase shift. minus pi over 3 radians. Okay, and now here, I know for most of these I've been graphing in chunks of pi over 4. And here I just use chunks of pi over 3 because I'm graphing kind of a simple sine function, right? I know I'm just graphing a sine function, so I already know what the general shape of a sine function is. So I don't need a whole lot of points to estimate between the points about what that's supposed to look like. I already know. And since I don't need a whole lot of points because I know this is just a sine function, I just used pi over 3 as my x increment, right? Each time I go up by pi over 3, just to simplify the graphing. So I only have 7 points here, right? But ordinarily, especially if it's an equation that I don't have a good idea of what it looks like or how to draw the lines between the points. And a good example of that would be like secant or cosecant functions, right? Or tangent, because remember, they have really weird shapes where they go off to vertical asymptotes and extreme values, all that sort of thing. So you don't know how to approximate the lines between the points on those kind of functions. Because of that, you need to add a few more points just to give you just to define it, at least at some of the points. Then your approximation where you're drawing lines between the points will have less error in it because you've got more actual points are actually plotted, so there's less guesswork. But again, ordinarily, if it's any kind of somewhat complicated function, I would use pi over 4 as my increment. And increment from what to what? So we're always graphing a fundamental cycle. And a fundamental cycle always goes from theta equals 0 to theta equals 2 pi. So we're always doing that. So we take the whole argument of the function, okay? And one cycle, this whole argument is going to go from 0 to 2 pi. And then we bust that up into equally spaced divisions from 0 to 2 pi. How many divisions? It's a little bit of an art or a arbitrary judgment. If it's some complicated function that you can't really visualize very easily, then you want a lot of divisions, right? So you can actually get quite a few of the points marked down exactly what they are, and then your approximation between the points is going to be better when you're just sketching it in. If it's a simple function, you don't need so many points because you know the shape already. So that's what I did here. I used pi over 3 because that was our phase shift, so it just naturally suggested itself as an increment. If I know this is my phase shift, I'll just go in divisions that are that big across here. And then I only have 7 points, but I know it's a sine wave, and actually it's a negative sine wave. Okay, so you get theta, you go from 0 to 2 pi, you pick how many increments you want to use. Usually I'm going to use pi over 4. If they're just doing a sine function or cosine, sometimes people even have pi over 2, 2 pi over 2, 3 pi over. They only have 5 points. They just go in pi over 2 jumps because they know what the function looks like. For us, a lot of times we want to use pi over 4, so that would give you 9 points until you'd start out 0, pi over 4. Then you'd get up here 7 pi over 4, 8 pi over 4, which is your 2 pi, right? And that would give you 9 points for theta, 9 different divisions. Okay, so that part's easy, involves a little judgment. What are we going to use as our interval? How many divisions do we want over this 2 pi range? We've answered that. Okay, x is a simple calculation. You take the argument, okay, and we've said that argument is theta. Well, you still can't see it. That this argument is theta, right? The whole thing is the angle. So this whole thing is theta. And so we just set Let me write it over here. I did this on other papers, but so we got theta equals x plus pi over 3, okay? So that's what theta is, and we've done theta in this column. Well now, but when we make the graph, we're graphing the x value with y, and y, remember, is the whole function, it's everything. Okay, so we have to get the actual x value for our point. Our point's going to consist of an x value and its y value. Here, y is 0, so this is an x value with the y value, another x value with the y value. And so here's our whole argument of our sine function, or it could be of a cosine function. So that's what theta is. So then we just rearrange this to have x on one side of the equation. Then we know what x is. So here, to solve this for x, we would just subtract pi over 3 from both sides of the equation. So theta minus pi over 3 equals x plus pi over 3 minus pi over 3. So these pi over 3s plus and minus would cancel out on this side of the equation, and you'd be left over here with just x minus pi over 3. So that's what we have. This is what we're left with. We just solve our equation. We have theta equals some function of x. We just solve it in reverse. We just want to know what x is. So you just isolate x on one side of the equation using your standard algebra rules. If you can add something to an equation, as long as you add it to both sides, you can subtract as long as you do it to both sides. And the reason you have to do it to both sides is if you do that, this equal sign never changes. It's always still true, right? I could add 50 to this and add 50 to this, then this is still true. So that's why you have that rule. And then it's also true for division multiplication, right? I can divide this side by some number as long as I divide this side by that number. So, but these are usually pretty simple. Usually they're just a couple terms like this, and you get here, just in 1 or 2 steps. So we know what x is. X is theta minus pi over 3. So now you just plug your theta value in. We have a pi over 3. So remember, that's theta. So if I plug pi over 3 in for this, pi over 3 minus pi over 3 is 0. So when theta is pi over 3, x is 0. So I just put the value of x here. Then I plug the next value for theta into this equation. 2 pi over 3 minus pi over 3 is pi over 3. So when theta is 2 pi over 3, x will be 2 pi over 3 minus pi over 3, which is just pi over 3. So, and here it is. So we just fill in the column of the table. So the x is, it's just a mechanical, just, punch and crunch. You put the number in, turn the crank. For this theta, what's x? Just plug theta into the equation. That tells you what x is, and then just write it down, and you're done. Okay, then your graph, you're graphing x and y. So we just, and what is y? Well, y is this whole function, right? It's everything. So sometimes you might want it like here. It's easy to do this in steps. Instead of just writing y, sine theta, we get very easily and very fast. And remember, so sine theta, this whole thing, since we said this whole argument is theta, then sine of theta is a simple thing. It's just a sine of an angle, right? We go back to our wheel and we say, well, here's different thetas. So we can get sine theta very fast. We look up, if we're going in chunks of whatever chunk we're going in. This problem I went in pi over 3. So we start at 0. And remember, sine is always the second value in these pairs, right? Because this is, in these pairs, this is cosine of theta and this is sine of theta, right? And when we're on the unit circle, so if this radius is equal to 1, then this thing is a unit circle, okay? If we're on a unit circle, then this first number is the x value for this point. The second number is the y value for that same point. So this is just x and y for these points on the circle, if it's a unit circle. But whether it's a unit circle or not, this first number is always the cosine of theta, the cosine of this angle. It doesn't matter if this is a unit circle or something bigger or smaller than a unit circle. This is always cosine of theta. This is always sine of theta. So we can go around here, pi over 4, and we can get the sine value, 1 over the square root of 2, for whatever angle we want. So we get that pretty quick, right? When we go through this process here. So we've got theta x, so let's just record sine theta. So we just plug we get our angle, what theta is, and it's always going to be an angle from that wheel that's already spelled out for us for our problems. And it'll be either pi over 4 or a multiple of that, or pi over 3 or a multiple of that. All these angles, we get them from the wheel. We just plug this angle into the sine function, and from the wheel, it tells us what that value is. We just glance at it and write it down immediately. Now, when we're graphing, we need a number on this x, right? It's hard for us to think about, well, what is this number? If this is 2 pi over 3 and this is 3 pi over 3, we know, well, maybe we're, a third of the way between here and here, but what's that actual number in order to be able to graph it? So what you do is you just write down the approximate value for that in decimal. So just put that in your calculator, square root of 3 over 2, and write down about 3 decimals, which you're not graphing to that degree of precision, but just so you know what it is. And I know this number here would be about 0.87. So in your scale here, we're going to look for about 0.87, right? Which would be about right here. So this midpoint would be a half, 0.5. And we go, let's see, I got to see if everybody's admitted here. Hopefully I didn't lose Alexis. That's the thing I got to remember about Zoom. When somebody comes on, I have to go up and click admit button. And I'm not sure, I guess I did that with yeah, okay. And now I don't see Alex, so he's having trouble. He's coming on and going off. All right. So back to this, theta, again, we pick our increment based on, we have to think about, well, how big do we want these divisions, which is basically how many points do we want to get to approximate this. The more points, the better your approximation. If it's a simple function like sine, you don't need a whole lot of points because you already know what the shape is, right? And just maybe write down what some of the critical values of points are. Then we got x. We start with what the argument of the function is. We solve for x, and then we just write those down. They're quick. Once we have this little equation, we just it gives us x. Then sine theta we get from our wheel. Here's the wheel. So you go around, these are different thetas, and sine is always the second number in the pair is the sine of theta. It doesn't matter if this is a unit circle or not. Write down the sine of theta. And then what we're plotting in the graph is we're plotting x and y, which is the same thing as f of x. And f of x is the whole function, the original function. So our original function was minus the sine of x plus pi over 3, okay? But we already know that this x plus pi over 3 is just theta, and we've already got sine of theta here. We've already done that work. So the only thing that's going to be different about y than sine of theta is we notice the equation that we're doing has a minus sign in front of it. So we get our value from sine of theta because negative sine of x plus pi over 3 is negative sine of theta. So we've got sine of theta, we put a negative sign on it, and we're done. We have y. So now we have our x points and we have our y points, and then we just draw a graph and draw the points in, and then we estimate with our eyeball and from our knowledge of what a sine or cosine function is and draw in the rest. So that's that problem. Let's go to the next one. Okay. What we're going to graph now is y equals cosine of the quantity 3x minus 2 pi plus 4. So we compare that with our standard form, which looks just like it did for a sine function. It's just we're using a cosine instead of a sine, but they're no different. The form's the same. It's a times the function of the quantity. The argument is omega x plus phi, and then outside that we have plus b, which is our vertical shift. So we want to identify a, omega, phi, and b from our equation. Okay, we've got a little issue here with this equation. For one, we see what's a. Well, there is no plus b. So this is understood to be 1. So this is y equals 1 times this cosine function, because 1 times something doesn't change it. It's the same value. So our a is just not stated, but it's there, and its value is 1 for a. Okay, let's look inside the argument. We've got what looks like an omega x here, but then we have minus something. And our standard form says plus b. Okay. This isn't b here because our standard form is omega x plus b. And we have something, a positive number times x minus something here. So this is not phi. How do we resolve that? Well, we recognize that we can rewrite 3x minus 2 pi. We can rewrite that this way. We can say 3x plus a negative 2 pi, because plus a negative 2 pi is the same value. It's the same thing as just subtracting 2 pi. So this is rewritten. But now this tells us we can get phi because our standard form is plus phi. Well, now we have a 3x plus something. So whatever this thing is being plus is phi. So phi is minus 2 pi. Okay, so now we've got phi. It's minus 2 pi. Now we can write down, we said a was 1, because there's nothing there, so that's the same thing as 1 times that. 1 times cosine is still just cosine, so they're equivalent. So there is an a there, 1. Omega is, and omega's always has to be a positive number, okay? And we have a positive number here, and it's 3, so that's omega. We call omega our angular frequency, okay? So that has to do with, all this is based on rotary motion of how fast the angle is changing when you go around that wheel, right? As theta changes, how fast is that angular change? How many radians per unit time? That's what omega is. Earlier in the course, we called that angular velocity, and now we're saying frequency. So what's up with that? Well, in physics, there's a thing called a vector representation of a number and a scalar representation. So a vector, there are 2 things associated with a vector. A vector has a magnitude, a size of the number, and a direction. A scalar only has magnitude. So an example, that's regular velocity. Velocity would be 60 miles per hour east. So it's the magnitude of the speed, if you will, and the direction of it. That's velocity. speed is a scalar. It's just a magnitude. It's 60 miles per hour. I don't care which way you're going. This is how fast you're traveling, but I haven't told you anything about what direction. That's the way it is with omega, okay? Omega is here, we're going to always be using it as angular frequency. So in frequency, we don't specify direction. Are we rotating counterclockwise or clockwise? We don't really specify. So what we say is omega always has to be a positive number. And if omega is always a positive number, then we call it a frequency, okay? So it doesn't tell you anything about the direction per se, but we know from standard form that positive is a counterclockwise rotation. But so frequency is like, for velocity, well, yeah, angular frequency is like saying angular speed, okay? And so angular velocity and angular speed are the same thing. It's just when you say angular velocity, you would have to state, clockwise rotation or counterclockwise. Angular frequency, just how fast is this thing changing? How many cycles are, and that's what frequency is a measure of cycles per second, okay, which is also called hertz. 1 cycle per second is a hertz. And so angular frequency, just how many cycles per second, has nothing to do with your starting point. Are you going up and back to 0 and then negative, or are you going negative to begin with, back up to 0, positive, and then back to negative? It doesn't matter. It's just for any starting point you have for a repeating function, how many cycles does it do in a unit of time, and usually it's per second. So anyway, I know that's a lot, but the point is omega always has to be a positive number when we're talking about standard form. So we're not talking about direction of anything. We're just talking about how many cycles per second, or how many radians per second actually, because the relation is here, omega is 2 pi f, okay? So if I have 1 cycle per second, we know there's 2 pi radians in 1 cycle. That means I've traveled 2 pi radians in a second, right? If f is 1. So if f is 1, omega is 2 pi. So omega is how many radians you change per unit time. If I have a higher frequency, that's more cycles per second. And what's a cycle? A cycle is like a complete revolution. So 2 pi is 1 cycle, right? So f is just how many cycles you're doing in a second times the length of 1 cycle. This is a length, that's an angular length, if you will. How many radians 1 cycle is times the number of cycles per second gives you how many radians per unit time, which usually is seconds, but it could be other values. So that's omega. Okay. All right. Phase shift is minus phi over omega. Now, we went through this thing where we said phi is not 2 pi because it has to be in the form plus phi. And we went through this and said, well, minus 2 pi is the same thing as plus a negative 2 pi. Now we're in standard form. Phi is minus 2 pi. So minus phi is minus, there's the minus, then write down what phi is. Phi is minus 2 pi itself divided by omega, which we said always has to be a positive number, 3. So negative, a negative is a positive. So our phase shift is 2 pi over 3, and that's radians. That's an angular change. How many radians did that thing move horizontally, okay? And then in this equation, we actually have a b now. Here's plus outside of this function, plus some constant, plus b. B is 4. B is the vertical shift. That's going to move our function this way when we plot it. It's going to give us a different y value. This will be the midline of the cosine function. So when we graph this, we know that the zero value, if you will, for our function in the graph is actually going to be 4 and not 0. It's going to oscillate around the number 4 on the y-axis. Okay. So we've got all those parameters. Now here, this was again more of a complicated looking thing. So more of a complicated looking function. So because of that, let's see, well, it's almost 9 o'clock. Alex, I was saying at the beginning of this lecture that I'm going to go through all these problems now, so that's probably going to take a while. But if you need to leave, that's fine. I will post this video on Blackboard, a link to it today, so you can come back and watch this at any time. But this is all the homework problems that were assigned on Friday is what we're doing here. And so if you need to leave, feel free to, and I'll just keep going. I'll record this. I'm going to post this whole thing online. You can go back and watch it. Okay, so we're graphing this function here, which is a little bit more complicated. Just from glancing at it, I'm not exactly sure what this would look like in the graph, just from trying to do it in my head really fast. Because of that, I want to get a few more points of the actual function itself. So we always go from theta to 2 pi theta. Or I'm sorry, we always go from theta equals 0 to theta equals 2 pi. And then we divide that up in divisions, equally spaced divisions. How many divisions? It depends on how well you want to approximate the function. And for us, this will always be enough. If we go in pi over 4 jumps, that'll give us enough points to see generally what the function's doing. If it's a very simple function like a plane sine or plane cosine, we might just do pi over 3 or pi over 2 chunks. Then we don't have as many points here, all right, in our graph, but we already know what the function looks like, so we just get a few points and kind of draw between the lines. Here, this function that we're doing is a little more complicated looking, so we want to get more points in order to have a better approximation. So we use pi over 4 chunks. That's our increment in x, okay? Well, in theta, that's our increment in theta. And theta for one cycle always goes from 0 to 2 pi. So 2 pi will be written differently depending on what kind of chunks you're using. Since we're using pi over 4 chunks, 2 pi will be 8 pi over 4. This is 2 pi. So each time we go pi over 4 more, okay? If we were going in pi over 3 chunks, this would be 6 pi over 3, because that's 2 pi. So we go from 0, pi over 3, 2 pi over 3, 3 pi over 3, up to 6 pi over 3. Or we could be going in pi over 2 chunks, right? 0, pi over 2, 2 pi over 2, 3 pi over 2, and then 4 pi over 2. Well, that's 2 pi, and you're done, but you only have 4 points. So we're doing pi over 4 chunks. So we just write those down. Then cosine theta, we get, what did I do with it? My wheel. We can just look at the wheel, and the cosine is always the first value in these pairs, right? No matter if this is a unit circle or not. Well, actually, yeah, I need to restate that a tiny bit. If it's a unit circle, this is this cosine theta. If it's not a unit circle, this is r cosine theta and r sine theta. So I guess this one actually has to be the unit circle. So I misspoke earlier. What I was saying earlier is this, on a unit circle, this point, okay, this is the x coordinate for the point on the circle, and this is the y coordinate, right? For a unit circle, these are the values. If we were not on a unit circle, this number would be r cosine theta. So r would not be 1, r would be some other number. So this number would actually be different. So I said that wrong earlier. These numbers will change if you're not on a unit circle because r is different. It's always r cosine theta. This is your x value, and r sine theta is always your y value. That's always true. On a unit circle, r is equal to 1. So this just becomes cosine theta and sine theta. That's why we use this. We can look up an angle, and this is the unit circle. We have our cosine value for that angle and our sine value, all these pairs. If we're not on a unit circle, we have to multiply r times this number to get what the x coordinate is, and r times this number to get what the y coordinate is. So need to correct that. All right. But in graphing, we're just using this to pull off our cosine values really fast, right? So we can just look up our angles, get the first number, that is the cosine of that angle. So we get those really quick. We just write them down. Okay, and then we need x. I need to put a parentheses in there. So Alex, to get x is pretty straightforward. Remember, in our original function here, what's inside the parentheses, this is called the argument of the cosine of 3x minus 2. The argument of that is 3x minus 2 pi. The argument is an angle, so we call it theta. So this whole thing is theta. So to get what x is, we just write down, well, here was theta. Theta was the argument of that cosine function. So theta is 3x minus 2 pi. And then we solve this for x, right? We just want to get x isolated on one side of the equation. So we would add 2 pi to both sides. That'll cancel out over here, and we'll just have 3x will be equal to theta plus 2 pi. Then to get rid of the 3 over here, we just divide both sides of the equation by 3, and then the 3's cancel. And we have x equals theta plus 2 pi over 3. Now we know what x is. We have theta already, so we just plug in our theta value to this equation. Theta equals pi over 4 plus 2 pi, add that together, divide by 3, and you would get 9 pi over 12. And I did it over here. Theta plus 2 pi. So for this first value, pi, well, it's the second value. The first value, theta is 0, right? So if theta is 0 here, we plug in 0, x equals 0 plus 2 pi over 3. So x is 2 pi over 3. That's our first value. Second value, theta is pi over 4. So we plug pi over 4 in for theta. And we add 2 pi to it. Well, we got fractions. We need common denominators. So we say pi over 4 plus 8 pi over 4. This is the same thing as 2 pi. We have 9 pi over 4. Okay. But now this, from our question, so we have 9 pi. This part is 9 pi over 4, but it's divided by 3. Okay, so we just simplify this, combine terms, and we have 9 pi over 12. Now, ordinarily, you would simplify that, right? You'd say, well, that's 3 pi over 4. But we're going to end up, all the values we're going to get are going to be something over 12. And some of them, for example, 13 pi over 4, that doesn't simplify very well. So because of that, or 11 pi over 12, you can't reduce that at all. It has to be 11 pi over 12 when you're done. Because of that, we just write all of these as something over 12. So we've got apples and apples the whole way down. It's always something divided by 12. I didn't do that on the very first one, but you can see here 2 pi over 3 would be the same thing as 8 pi over 12. And you notice there is a pattern here, right? We went from 8 pi over 12 to 9 pi over 12. When you plug this theta, 2 pi over 4 into this equation to see what your next x is. Plug in 2 pi over 4 and do this. That gives you x. Okay, here's our theta, 2 pi over 4. The x we get for that is 10 pi over 12. So you can see there's a pattern. We had 8 pi over 12, 9 pi over 12, 10 pi. So we're going up in equal jumps in x when we're going in equal jumps in theta. So we don't have to calculate all of these now. We can just write 11 pi over 12, 12, 13. We might calculate this one just to make sure we haven't made a mistake, that that pattern is true, that it holds up for the whole thing, right? So let's do 7 pi over 4. This would be plus 8 pi over 4. Well, that would be 15 pi over 4. 15 pi over 4 divided by 3 would be 15 pi over 12. And that's what it came out to be. So that pattern does hold up, okay? So once you figure, if you're going in equal increments here, once you figure out what the increment is in a couple of these, you can just continue that, just add another increment each time, and you're done. You don't have to calculate, you know, every single step for x. You've got it. After you've done about 3 of them, you can write all the rest of them down. Maybe do the last one just to make sure you didn't make a mistake, right? So now we can graph it. And what you're graphing is you're graphing x and the points x and y, right? Right here. This is what you're graphing, which is the same thing as x and f of x. And f of x and y is given here. So we're graphing, we get an x value and then we get a y value, and a y value is the whole function, okay? All right, so we had these 3 columns, and then we just write down, okay, and we notice this part here is not as complicated as it looks, because this cosine of this complicated looking thing, 3x minus 2 pi, well, this thing is theta. We said that the argument of the function is theta. We've already got cosine theta done here. So we've got what cosine of this thing is. It's cosine of theta. So to get y, we just take cosine theta plus 4. Well, here's cosine theta. So we just add 4 to each one of these, and this is what we get. Okay, so we have 4 plus cosine theta, which is 1 over square root of 2. Now we're graphing it. Okay, so 1 over square root of 2 is an exact value, but when we're drawing a graph, we need a number, right? Because we're going to make a scale and we need to know where to put the point. So we get an approximation of what that, we just plug this into our calculator to get a decimal approximation for this exact number. So if you just do this on your calculator, add 4 plus 1 over the square root of 2, and write down about 3 decimal places. Now our graph isn't this precise, but this is just going to give us an idea on the graph where to put this point. It's going to be somewhere around 4.7, you know, just a hair more than 4.7, or 4.7 may be close enough for our eyeball. But write down 3 digits here as your approximation for this, of how accurate you're going to be. And then when you graph it again, you're not worrying about all of these digits. You're just doing this so you can get a good idea of where to approximate the point on the graph. So 4, we don't need to do anything. We've got this thing, 4 minus 1 over the square root of 2. So we wrote down approximately what it is. And notice, since it's a cosine function, it's cyclic, it's going to repeat. So we have the same values in this table in several places, right? So I've done this once. I can just look down. Oh, I've already got that. I put that here. I've done this once. Oh, I've already got that. I write it here. So that gives you your table. You know, it takes a little bit of time, but it's nothing really difficult. It's just a little bit tedious. So we graph that function, okay? And again, we get the points x. So here's our first x value, which this would be 8 pi over 12, right? Since all these are in 12ths. And then we get our y value, which is our whole function, and it's 5. So we plot these 2 points. Or I say these 2 points. This pair is a single point on the graph, right? That's its x value and that's its y value. And you just go draw yourself up a graph. And here's the graph of that function. It starts here and ends here. And the period is the length of one cycle, right? If it wants to know the period. So the period, because this thing would repeat. You'd have the same function again here, and you'd have the same function here. This is just one cycle of it, right? The period is any point to that same point on the next one. So like if this, was repeating here, so the period is from here to here, but I could have just as easily started here and said, what's my period? Well, it's the distance from here to when you get that same occurrence in the cycle again, right? Which would be here. Well, this distance is the same as this distance. So this is one cycle of this function. So its period is 16 pi over 12 minus 8 pi over 12. So it's 8 pi over 12, which is 2/3 pi. That's its, and I like this function. It's a seagull, right? Looks kind of like a seagull there. A Jonathan Livingston function, we'll call that. So that's that problem. Let's move on. Okay. Here we have y equals minus 3/2 times cosine 2x plus pi over 3 minus 1/2. So we compare it to the standard form, a cosine omega x plus phi plus b, and we see that our a is negative 3/2, okay, from this form. A something times cosine, negative 3/2 times, so that's a. Our amplitude is the absolute value of a. Absolute value of negative 3/2 is 3/2. So that's the peak height. That's how tall the peak's going to be on the sinusoid, plus and minus, right? And our omega is easy to get on this one. This is already in the right form. It's something times x plus a number. So we've already got the form we want and need. So we just read it off. This 2 would be omega. So this is the angular frequency of the function. It's 2 radians per unit time, which usually they use seconds. But that's how fast the angle's changing, right? So we write down omega. And here's, again, omega is 2 pi times the frequency. But we just need omega. But this is how, when you hear that word frequency, that's how you can relate that to omega. That's one of the reasons this is called angular frequency. Number of cycles per second times the length of one cycle gives you how many radians per second, right? Okay, and phi, we've gotten standard form already. It's pi over 3 radians. So this is going to shift this function to the right by pi over 3 functions, okay? So where a cosine would normally start, a cosine function normally starts at 1, at 0, and then drops down. Well, this thing, instead of starting at 0, it's going to start over at pi over 3 and then have the same exact shape that a cosine because of this phase shift. Well, the phase shift is actually, I'm sorry, this isn't the phase shift. This is phi, but the phase shift is negative phi over omega. So if we take negative pi over 3 divided by 2, that works out to be, let's see. I think I did that. No, that's not right. This isn't right. This would be negative 2 pi over 6. This should be a 6 here. There's a mistake there, right? Negative pi over 3 divided by 2 is, wait a minute, no. It's negative pi over 6. There. I'm sorry, I messed that up. Negative pi over 3 divided by 2 is negative pi over 6. That's our phase shift, and that's in radians, okay? Oh, no, wait, I looked at that wrong. Okay, the vertical shift is negative 1/2. So that's going to move our graph this way. Okay, and what else do we have? Well, that's it. Okay, so we need to make the graph. Again, we're going to go, theta is going to go from 0 to 2 pi. That's one cycle. And this was kind of a slightly complicated looking function, right? It's not super simple. So to approximate it, we'll go in chunks of pi over 4. So we get a good idea of when we're graphing it. We'll go to that level of precision. Okay, so we go, theta will go from 0 to 2 pi in chunks of pi over 4. We're in increments of pi over 4. Then we need to know what x is. And so here's theta. Theta is the argument. It's the angle inside those parentheses. Theta is 2x plus pi over 3. So we solve this for x. So here we would say 2x equals theta minus pi over 3. We subtract pi over 3 from both sides of the equation, and they cancel out over here, and we just have 2x left. And now we want to divide both sides of the equation by 2 to get rid of this 2. So we divide this by 2. The 2's cancel. We just have x. It's this thing divided by 2. So now we can plug theta in. Pi over 4 minus pi over 3. Well, that would be 3 pi over 12 minus 4 pi over 12 is negative pi over 12, but it's divided by 2. Okay, so it's negative pi over 24. Yeah, which is here. I was looking at this one. That was throwing me because I was looking at 0. But pi over 4, we put in pi over 4 here, this second point here. And that is 3 pi over 12, right? And minus 4 pi over 12 is negative pi over 12 divided by 2 is negative pi over 24. So that's our x value for that point. And then we do the next one. Let's put theta of 2 pi over 4 in here. So this would be 6 pi over 12, right? That's the same thing as pi over 2. So 6 pi over 12, since we're working in things that have to do with 12s here. Then the reason of that is we're going in chunks of pi over 4, but the thing that we're having to add and subtract is something over 3. So to get a common denominator, we're using 12 here. So we're rewriting both of these in terms of something over 12 so we can combine them. So here, 2 pi over 4 would be 6 pi over 12 minus pi over 3 would be 4 pi over 12. So we've got 6 pi over 12 minus 4 pi over 12 would be 2 pi over 12. Okay, and we divide that by 2, we have 2 pi over 24. And that's what this came out to be. Okay, and when we do the next one, we get 5 pi over 24. And then 8, so you can see if we're going up the same increment in theta each time, there's a pattern here. We'll go the same increment in x, whatever it is. So when we went from negative 4 pi over 24 to negative pi over 24, we increased by 3 pi over 24. And notice that's what happened when we calculated the next one. We increased by 3 pi over 24, because when we go from negative pi to plus 2 pi, we've increased by 3 pi over 24. So each one of these is going to increase by 3 pi over 24. So from 2 to 5 to 8 pi over 20 to 11 to 14, 17. And then this last one, this would be 20, right? 20 pi over 24. And we can check ourselves and make sure we didn't make a mistake. So let's calculate this last x value, and for this pattern to be correct, this would have to come out 20 pi over 24. So let's calculate what x is when theta is 8 pi over 4. So we put 8 pi over 4. That's the same thing as 24 pi over 12, right? Multiply top and bottom by 3, 8 over 4 times 3 over 3 is 24 over 12. So 24 pi over 12, yes, minus, this would be 4 pi over 12. That gives us a total of 4, okay, 24 pi over 12 minus 4 pi over 12 gives us 20 pi over 12 divided by 2 gives us 20 pi over 24. That's what this comes out to be, 20 pi divided by 24. And that is, if we multiply both of these times 4, which is multiplying times 1, we get 20 pi over 24. So our pattern's right. We went another 3. We went from 17 to 20. So going backwards, 20, 17, minus 3 is 14, minus 3 is 11. So I'm just saying, you just do a couple of these x's and you see how big the increment is, and you can just add that increment each time. So we were using 24s here. So we've got theta, we've got x. Cosine theta we get from our wheel. We go around the wheel and pick up our values, which is the first value in the pair on that wheel. Right, so here's pi over 4. Here's pi over 4. So the cosine pi over 4 is going to be 1 over square root of 2. So we just write those down. And now here we write down y, what the whole function is, okay? And notice we've already got cosine theta. So we just take minus 3.5 times this value times the cosine theta value. And then we subtract 1/2 from that. When you do that here, minus 3.5 times 1 is minus 1.5, minus another half is -2. Minus 3.5 times 1 over the square root of 2 minus 1/2 gives you, and you just have to do that on the calculator, okay? Just plug this into your calculator. Multiply this times 3, divide by 2, put a negative sign in front of it, then subtract 1/2 from that, and that gives you this y value here. And I just put 2 digits there because we're going to just, graph it. We just want an approximation. And you do that for each point. You get cosine theta, multiply times -3/2, subtract 1/2 from it, and that gives you each one of these points. So you just get this point and plug it into this, and that gives you this point. Then our graph is always, it's x and y. Then we make a plot. So here's the plot of this function. So let's look at this here. I didn't write, for some reason on this one, I didn't write out the scale. Very fine in detail. These are, so we're going from minus 4 pi over 24. Okay, so this point here is minus 4 pi over 24. And that would be our first point on our graph here, okay, which is -2. And then our end point here, this is 20 pi over 24 is our end point. I'll just put this down here. Minus 4 pi over 24. That's this point here. So each one of these, we're going from -4 to +20. So we're going a total of 24 pi then, right? Because we go 4 pi to get up to 0. And then we go another 20 pi beyond that. So we've got a total distance here of 24 pi over 24, which is pi. So the period for this function, period, is this distance from here to here. That ends up being pi. Okay. So this is just supposed to be showing you the axis. That's not a data point. So there's notice it looks like a cosine function, except because we had this minus sign here, where that's minus, the cosine function would actually be a mirror image of this, just a regular cosine. So flip this thing over the x-axis, reflect it over the x-axis. So the cosine, regular cosine function starts and drops and then comes back up, right? But because we have this negative sign on our function, that rotates it about the x-axis. And then because we have this -1/2, this is your vertical shift, it moves the midpoint. So instead of the midpoint being the x-axis, which you could see it's not here, right? Because more of the function's below this y equals 0 than is above y equals 0. But that's because we have this vertical shift -1/2. So that moves the midline of this function down by 1/2. So this function, the midline, would actually be, about through here. So that's what the vertical shift does. It moved our, first of all, we reflect the regular cosine because we had a minus sign. So that makes it upside down, if you will, reflects it across the axis. But then after we reflect it, we move it down by this 1/2. So that makes the midline, the middle of the function in terms of y, about right here, where y equals -1/2. And then our phase shift, we said, was minus pi over 6. Well, guess what minus pi over 6 is? That's the same thing as if we multiplied top and bottom by 4, right? Because minus pi over 6 times 4 divided by 4. So 4 divided by 4 is 1, right? So if we multiply this times 4 over 4, we have not changed the value of it. But we rewrite it as -4 pi over 24. So that's our phase shift. Well, look where our function started. It started at our first x point that we have is at -4 over 24. That's our phase shift. So the cosine function ordinarily would start at 0. But now we started it back here at -4 pi over 24. So that's showing you what the phase shift did. It moved the whole function to the left. So the negative sign did a mirror image of a cosine. Our phase shift moved it to the left by 4 pi over 24. And then our vertical shift moved the thing down by 1/2. So the midpoint of the function is -1/2. All right, that demonstrates all of these parameters in the standard form on that problem. Okay, next we have problem 12. We're going to graph 4 times sine of -2 pi x plus pi. Well, you can't see that, sorry. There you go. All right, we're going to graph this. Here's the standard form. You notice we got a problem right off the bat, okay? And this one would be tricky. It would take you a while to figure it out. So I'll help you with it, all right? The problem is that we got this minus sign in front of a number that's in front of x. In our standard form, we said omega is going to represent a frequency. So that's always a positive number. Omega has to be greater than 0 always, but we got a negative number. So we have to rewrite this thing somehow where we don't have a negative number in front of the x. But we have to be very particular about how we rewrite it, because we can't just change it into anything we want it to be, because we've changed its value. We're not allowed to change the value of this thing. We can rewrite it to where it looks different, but its value, its numerical value, if you plug in any x, has to be the same exact value as it is for this thing. But we're not in standard form. So how do we get there? Okay. Well, some ideas you might think about is immediately you think, well, that needs to be a plus sign. So let's just multiply by -1, right? And make this a plus 2 pi. Well, if you did that, if you just multiply this by -1, you've changed it, okay? It's got a different value now than what it had before. You're not allowed to just change that to a plus sign because you need it to be a plus, because you change what it is then. And we're graphing this function, right? So we can't just multiply that number by -1 to get what we want, because it changes the angle. Okay, so we're allowed to manipulate a function as long as we don't change the value. All right, we've explained that. So here's what we have, and here's the standard form. How do we change from -2 pi to plus 2 pi, which is what we need to get it in standard form, okay? And we've shown here that we can't do that. We just talked about that because we got a different animal, and we're not graphing the thing we're supposed to be graphing. We can't just change it. What if we change the whole angle from a negative to a plus? So remember, the argument is theta. The argument is the total angle, right? And our problem is this is negative and we want positive. Well, if we change this whole angle, change the sign on it, let's do that. Let's put a negative on this whole angle. Well, that changes both of these terms, okay? So that gives us, now we have a positive 2 pi x, which is what we want, but we have a negative pi, okay? So that's better, but we still got an issue, a similar issue. We just made a change in a different place. So if we multiply the whole angle by -1 by a minus sign, we're not talking about theta anymore. Now this thing is not theta, it's negative theta. Because if we multiplied this times -1, we had to multiply theta times -1, right? Because this theta equals this angle inside the parentheses. And if we do something to this, we got to do it over here too. So now we've got negative theta. So we still got a problem because we don't necessarily want to graph negative theta, right? We want to graph our original problem, which is theta. So how do we resolve that? Okay. Because, well, we know we can't just make it a negative theta because the sine of theta is not equal to the sine of negative theta. So that's an issue. We've changed the value if we just make theta negative, okay? But we can use a theorem from earlier section in the book, okay? It's Theorem 10.12, and these are called even-odd identities, all right? And there's a list of them there. It'd be good for you to have a look at them. But the one we need, you notice this form that we're wrestling with here. I don't know if you can see that there. We're wrestling with this. You know, we can't do it because we've changed the value. But we notice this theorem looks kind of like that, right? Here we have a theta inside, but we have a negative theta over here. But it's different. We got an extra negative sign out here, okay? But this equality holds. This is true. The sine of theta is equal to negative the sine of negative theta. That is true. So we can make use of this to rewrite our function, okay? So if we changed theta to negative theta in our original function, remember what I said, you're allowed to write something in a different form as long as you don't change the value of the whole thing, all right? So if we change theta to negative theta, but we also, when we do that, if we also add a negative sign outside of it, then we haven't changed the whole thing, because this equality still holds, because sine of theta is equal to negative sine of negative theta. Okay, so we're allowed to make this change because we have not hurt this equal sign at all. It's still true. So we can rewrite our function. We had a sine of some function. We can rewrite it as a negative sine of the negative angle, and its value stays the same. We're allowed to do that, okay? Let's do that then. So we can, here's our problem, and our problem was we wanted this to be a positive number in front of the x in order to get our omega that we need for our standard form. So theta is this whole angle minus 2 pi x plus pi. Here's the function, 4 times the sine of that, okay? And now here, what I've done is I've inserted negative theta. If this is theta, then negative theta equals negative of minus 2 pi x plus pi. And when you do this multiplication, you get a positive 2 pi x minus pi, which is here. So I've started with sine of theta. Now I have negative sine of negative theta, right? Because we said this thing, which is this now, is negative theta. All right, I'll write that up there just so you see it. So again, we're using this theorem is why we're allowed to do that. Sine of theta is equal to negative sine of negative theta. That's what we've done. So we've rewritten 4 times the sine of theta is 4 times the negative sine of negative theta. And that gives us this. Now we've got a form we like better. We can get our omega now. Now this omega would actually be 2 pi, right? It's everything in front of the x, and it's got to be positive. Well, 2 pi is positive. That's a number, right? 2 pi is a single number. So 2 pi is omega. Now we have, we've introduced another small problem that we've seen once before in an earlier problem, though. Our standard form, let me go back to our standard form, says omega x plus phi, right? And we had this problem earlier. Now that we've changed this thing, because now we have, here's omega x, but our plus phi is minus pi, and we're supposed to have a plus sign in our standard form, right? So can you see that? Yeah, here. This camera, it doesn't show the whole page, and I keep thinking you're seeing everything, and maybe I haven't moved it enough. So just to make sure you saw that. So we started out with theta, and we changed that to minus theta. So minus theta is the negative of this. The negative of this thing is actually a positive 2 pi x, but then minus pi. Okay, so now we've rewritten this as sine of theta equals 4 times negative the sine of negative theta. This is negative theta inside here. Okay, and so, and then looking at our standard form, we have plus phi. We got a problem here because now we have a minus something, but we've dealt with this before, right? We want that to be a plus something, but it's minus pi. So we notice that we can rewrite negative pi as the same thing as plus a negative pi, right? But that just tells us then we have phi now, because from our standard form we're plus phi. So plus, so this whole thing is phi. So phi is not pi, phi is negative pi. So this, not written in standard form, we rewrite in standard form here, the argument 2 pi x plus negative pi. So phi from standard form, omega x plus phi, there's omega s plus phi is negative pi. And we're done. We got everything we need for this problem now. So here's a rewritten in standard form. Our b was 0. There was nothing out here, so that's the same thing as plus 0. So we can pick off all our parameters. A is -4. The amplitude's absolute value of -4, which is 4. Omega is the angular frequency. So this 2 pi is omega. It's a positive number, which we like. Phi, we have it in standard form, plus phi. So this whole thing is phi. Negative pi is phi. Our phase shift is negative phi over omega, which is negative, and then we put in what phi is. It's negative pi divided by 2 pi. So a negative 2 pi is positive pi, right? So we have pi over 2 pi. The pi's cancel out. So our phase shift is just 1/2. And that's our horizontal shift, okay? And it's a positive number. So it's going to shift the function to the right, I believe, by this number 1/2, okay? Yes, okay. Vertical shift, B, 0. So the function's not shifted this way at all. B is 0. So let's do our graph. We'll take theta in chunks of pi over 4. Okay, we need x. So here's what theta is now. And this is the original theta, right, which is what we want. We're graphing the original problem. So the original theta is this. We solved this for x. So x is going to be theta minus pi. That gets rid of the pi over here. Then we have to divide by -2 pi. Okay, so theta minus pi divided by 2 pi. But we had a negative sign, so we put the negative sign out here. So this is x. Here's the equation for x. So we take each theta value. 0 minus pi is negative pi. Negative and negative is plus pi. And plus pi over 2 pi is 1/2. Now, when we do the next one, well, let's go ahead and do the next one. Because we're using these chunks of pi over 4, let's do the next one. So theta is pi over 4. Pi over 4 minus pi is minus 4 pi over 4, right? So this would be negative pi over 4. Pi over 4 minus, pi over 4 minus 4 pi over 4 is negative 3 pi over 4, but then it's a negative that. So that makes it positive 3 pi over 4. No, then we have to divide by 2 pi. And so 3 pi over 4 divided by 2 pi, it ends up being let's see, 3 pi over 4 over 2 pi. I gotta write it down myself here. I'm losing track. Okay, theta pi over 4 minus 4 pi over 4 is negative 3 pi over 4. And negative is positive 3 pi over 4. So that gives us 3 pi over 8 pi. And I gotta pause the recording here.